Good morning. So today we're going to look at the work-energy theorem. We're going to see how when you do work on something, you change it, and the various ways in which the something, either an object or a system, can change will be how we define the kinds of energy that we transfer when we do work on something. So what happens when we do work on an object? Well, we apply a force over a distance, displacement of where the force is applied. But if work is the transfer of energy, then when you do positive work on the object, you increase its energy. And when you do negative work on the object, you decrease the energy. Now, keep in mind that work is just one of the ways to transfer energy. The other way to transfer energy is heating, which is broken down here into conduction and convection, and then radiation. So in this class, we usually say there's three ways to transfer energy: work, and conduction and convection, and then radiation. We will not deal with conduction, convection, or radiation in this class. We're going to stick to mechanical work. So this is the work-energy theorem. It just says that the net work you do on something is equal to the change in that thing's energy. And really, this is how we define the different kinds of energy things can have. Let's take the work that we do if we were to apply a force over displacement of a single object. So if you have an object, then the displacement of the object itself is the displacement of the point where the force is applied, if you have a point object, I should say. Because a point object doesn't have any dimension, so you can't displace where the force is being applied without displacing the thing itself. So the net work done on the point object is the work done by the net force. Now, by Newton's second law, the net force on an object is equal to the mass of the object times its acceleration. So the net work we do on an object is equal to its mass times acceleration times its displacement. Now, from kinematics, you might recall we do have a formula that talks about the acceleration times the displacement. This formula here, v final squared is equal to v initial squared plus 2a delta x. So if we move the v initial squared over to the left-hand side of that equation and divide both sides by 2, we have an expression for what a delta x is. And plugging that into the equation we have for Newton's second law, we get this. The net work done on a point object is equal to 1/2 mv final squared minus 1/2 mv initial squared. So if work is supposed to be the transfer of energy, then this has helped us define the first kind of energy we're going to look at. Because clearly what has happened to this object is it is changing from some initial state characterized by 1/2 mv initial squared, and it becomes a final state characterized by 1/2 mv final squared. So that 1/2 mv squared must be the kind of energy that the object acquires. And of course, you know that we call that the kinetic energy. It's the energy of motion, which is the only kind of energy a point object can have. So the work energy theorem for a point object says that the work done on the point object is equal to the change in its kinetic energy. And there it is in symbols. Now, eventually, we're going to use the work energy theorem to figure out different kinds of energy that can happen when you do work on a system. But if it's just an object, as we have seen, the only kind of energy it can acquire is kinetic energy. Let's see how this works in a practical application here. We've seen this example before. We have a force of 120 newtons pushing on a roller belt, and it pushes the box a distance of 0.8 meters. There's also a 5 Newton frictional force opposing the motion. And then the question we had to answer before was how fast, or we have to answer now, is how fast will the box be moving after this push? And the mass of the box is 30 kilograms. Well, we've already calculated one time how much work is being done on this box. The easiest way to do it probably is, in this case, just to take the net force, which is 115 newtons, and multiply that by 0.8 meters, and that gives us 92 joules of work being done on this box, which means the box must acquire 92 joules of kinetic energy. Now, if this starts from rest, we're going to, that's the assumption we have to make here. That doesn't give us that information up there, but we're going to assume it starts from rest. Then what you can say is that 1/2 mv final squared minus 0, because the initial is 0, must equal the 92 joules of kinetic energy that this thing has. And if you use that then to solve for V final, you'll find that it's equal to 2.48 meters per second. Go ahead and do that calculation right now just to confirm. Here's another example of the work-energy theorem applied to a point object. So in this case, the box is being moved up in a gravity field, but we're not going to use potential energy just yet. We'll come to that later on this week. Right now, we're just going to calculate the change in kinetic energy of the box by treating it as a point object. So there is a force of 80 newtons being applied to the box, and that is applied over a distance of 3 meters. So if we're to define the work done by the force, well, that is 3 meters times 80 newton, and the displacement is in the direction of the force, so it's a positive work, and that's 240 joules of work. Now, the box has a weight of 60 newtons. We're letting G is equal to 10 today. So the work done by gravity should have a magnitude of 60 newtons times 3 meters. But since the force of gravity points down and the box is moving up, that is a negative work being done on the box by the force of gravity. And so that is a negative 180 joules of work being done. Now it says find the final speed of the box. Well, we can calculate the net work that was done. We have 240 joules of positive work and 180 joules of negative work. So the net work that was done in this box is 60 joules. And if you plug that into the kinetic energy formula, assuming that it does say it starts from rest, and so that 60 joules should be equal to 1/2 mv final squared minus 0. And if you solve for that, you should find that the speed of the box after that rise of 3 meters is 4.5 meters per second. Go ahead and stop the video now and confirm if that's correct. All right. This one here, we're going to define average force using this idea. The average force, well, what does it mean to say that an average of something? An average is a number that you can use in place of all the specific numbers in your set and get the same ultimate result. Like, for example, if your average is 95% in AP Physics C class, that means that if every grade you earned in AP Physics C was a 95%, you would have that same average. That's the average you would have. So we can let 95% take the place of all of the actual grades that you have, because that is the same. We get the same result if we use 95% in place of your actual grades. The same kind of thing applies here. When this question is going to ask about the average force, what I mean is, what is the force that would accomplish the same total amount of kinetic energy being given to this golf ball when the golfer hits it? Clearly the force is not a constant, but there is some change in energy of the golf ball. And if we could calculate that change in energy of the golf ball, and we know the displacement of the golf ball, then we could just divide the change in energy of the golf ball by that displacement, and that should give us the average force. So the golf ball is initially at rest, and it has a final speed of 40 meters per second, and it gives us the mass of 0.045 kilograms. And we're going to assume that the displacement of the ball when it was hit by this club was 0.01 meters. In other words, the ball was in contact with the club over a distance of 1 centimeter. So calculate the average force exerted by the club and the ball. We're going to assume that this whole motion was horizontal, so there's no force of gravity doing work on the ball. The ball is not displacing in the vertical direction. Let's go ahead and calculate that out and see what results you get.